Hello everyone, this is Engineer Salase from Hello Academy and Brain Boosters, and today I came up with the other chapter 19. This is Translation Lookaside Buffers and TLBs. Let's get into it. So TLB, Translation Lookaside Buffers, these are part of the chip's memory management units. They are part of MMU and a hardware cache of popular virtual to physical address translation. So they help us to translate from virtual to physical address translation. So how this does, let's see. We have the CPU. The CPU will generate logical address. That means CPU will generate the virtual address. So what it does is TLB will look up in the memory management unit. Okay, so if in the memory management unit, if you find the virtual page number here, then it is called TLB. Okay, hit. We call it TLB hit. If it is in the TLB, then we call it TLB hit, and directly it will go to the physical address, and the CPU will get the data it needs. But the issue is, if there is a TLB hit, then there is no need to consult the page table, because we already found the address, and directly from the TLB we can found the physical address, and directly we can. The issue is when TLB miss occur, then if there is TLB miss, then there is a need to consult the page table. What it does is the TLB will go to the page table. This is the expensive process, because as you know, we have to look up all the page table, and all virtual memory should be checked, and p entries. So this address translation with MMU is like that. So if we have TLB hit, it's okay, well and good. Otherwise, if it is it's not in the frame, then TLB miss will happen, and the page table will be consulted. So the idea is, as you know, the memory is divided into frames. If the CPU wants that the virtual memory which is generated here, then if the page is not in the frame, then that will be a miss. That is in short, this is the idea. And we will see, we have a lot of algorithms, and LRU is the most popular. We will see it in the end, but this is the idea of the TLB. Okay, we have TLB hit, TLB miss, and if we have TLB hit, directly go to the physical address and fetch the data, and CPU will use it. Otherwise, if it is not, we have TLB miss, then we will go to the page table. So this is the TLB basic algorithms. Okay, so what it does is, as you know, we have the VPN, so the virtual address, and we have VPN mask. We did it in the previous chapter 18. I encourage you to go back and check this one. But what it does is, we have the virtual address, and we will do the VPN mask. After that, we will shift it by 4, and if it is success, then TLB entry is equal to TLB lookup the VPN from TLB, because it is success already. Then if success, then TLB hit will be happen. Then if can access, TLB entry protection bit will be checked, and offset is equal to, then once we know the VPN, then check the offset, that means the virtual address and offset mask. Okay, we have also the offset mask. Then find the physical address in the TLB entry, then found the physical frame number, the page number, then shift it, then offset, then access memory, physical address, otherwise raise exception. This is protection here. So as you can see, line 1, the line 1 is extract the virtual page number. Line 2, check if the TLB holds the translation for this VPN. 5 up to 8, extract the page frame number from the relevant TLB entry and form the desired physical address and access memory, the physical address and access memory. So in short, this is the TLB basic algorithm. And as you can see, VPN, virtual page number, TLB, translation, Lookaside buffer, and entry is not the same as page table entry. As you can see here, we look in the TLB, the lookup we have in the second code. What if, for example, else if TLB miss happen, what we do, page table base register, we have page table base register, and we have page table entry address. So the page table, because as you can see here, if it is not miss, we will check it in the TLB entry. But if it is miss, we have to go and check in the TLB page table entry. Okay, in the page table entry, because it's not in the TLB entry. So what we does, if the TLB miss happen, then we have to page table entry address is equal to page table base register we have, then this plus VPN size of page table entry, then PT is equal to access memory with the page table address. Else TLB entry, this will be translation Lookaside buffer, TLB entry is equal to VPN PTE, we have the page table entry, and we have frame number, physical frame number, then we have PTE, page number entry, and we will check the protection bit, then return instruction. So this one is for the miss case, TLB miss. When we have TLB miss, then we have to check it in the page table entry. But as we have seen here, if the TLB hit is here, there is no need to consult with the page table. We directly found the address TLB, then we directly go to the physical address, and the CPU will get the data, the frame it needs. So that is in a nutshell, this is the algorithm of the TLB, and the hardware access the page table to find the translation from 11 to 12. As you can see, 11 to 12, the hardware access the page table to find the translation, and 16 update the TLB with the translation, TLB insert. So this will be updated. So this is the algorithm. This is also the textbook. I hope I gave you some idea how the algorithm is working. So let's see an example now here. Very quick example. Accessing an array. How a TLB can improve its performance. This is the simple code. We have int sum 0 and for I from 0 to, we're gonna insert 10 arrays. Okay, I, as you can see, A is I, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 entries. This is an array. So let's assume, the assumption is we have 8-bit virtual address space, okay, and 16-byte pages, 16-byte virtual pages. This is a virtual page numbers, and thus 4-byte will be for the VPN because we have 8-bit. 4-byte will be for the VPN and 4-byte will be for the offset. Array A is loaded starting at the virtual address of 100. Let's assume this virtual address is 100, okay, virtual address, and it is 100. So when we change 100 into binary, 011001000 bit, so this is a virtual address. So the first 4, 1, 2, 3, 4 will be the VPN virtual page number 0110, and the offset will be the rest 0100. This will be the offset. And when you change it into decimal, 6. So 6 means this, the VPN is 06. And as you can see, since the size of an integer is 4 bytes, so it will load from 4 to 8. So this will be 4 bytes, okay, 4 bytes. And the TLB improves performance due to spatial locality. We will see what is spatial locality, but spatial locality will improve the performance. So in this scenario, if you check this load, we can see there will be 3 misses and 7 hits, okay. Thus TLB hit rate is 70%. In this scenario, the hit rate and the miss will be 3 miss out of this, and TLB hit rate is 70%. So this is also some how the access works. Locality means temporal locality. We have spatial locality and temporal locality. Temporal locality, what it says is an instruction or data item that has been recently accessed will likely be reaccessed soon in the future. So let's see this one, virtual memory. First access is page 1. So second access is also page 1. So this is the idea of temporal locality, okay. So the instruction or data item that has been recently accessed will be accessed soon as well. But spatial locality, what it says, if a program accesses memory at address X, it will likely soon access memory near X. So for example, in this virtual memory, first access is page 1, then second access nearby page 1 will be page 2, okay, it will be page 2. So that is the temporal locality and spatial locality. Who handles the TLB miss? Now that is the who handles the TLB miss. Hardware handles the TLB miss entirely on the CISC, that means complex instruction set computers. In this kind of computers, hardware handles the TLB miss. The hardware has to know exactly where the page table are located in the memory. The hardware would walk the page table, find the correct page table entry, and extract the desired translation, update, and retry instruction. So hardware managed TLB, that is one thing. And second type, that is the hardware. This is for the software managed TLBs. We have RISC. This is reduced instruction set computers have what is known as a software managed TLB. So on a TLB miss, the hardware raise exception, trap handlers, and trap handler is a code within the operating system that is written with the express purpose of handling TLB miss. Now let's see the same code. We have seen that, but TLB control flow algorithm. This is operating system handle. As you can see here, raise exceptions. So we have TLB miss. So this is how the operating system will raise. So go through this, the same code algorithm. Then TLB entry. TLB is managed by full associative method. That means a typical TLB might have 32, 64 or 128 entries. Hardware search the entry, the entire TLB in parallel to find the desired translation and other bits. For example, as you can see, we have VPN here, we have physical frame number here, and other bits. Other bits is valid bits, protection bits, address space identifier, dirty bits, all out. So this is typical TLB entry look like this. So let's see the issue of context, the issue TLB issues. What TLB issues? Let's see this one, context switch. Let's say we have process A and access virtual page number 10. Let's say virtual page number 10. So insert TLB entry like this, TLB table. We have VPN. We have page the physical frame number, and we have valid bits and protection bit like this. Now in the second scenario, let's say context switch happens and the same process B access VPN number 10. Okay, VPN number 10. So in the VPN number 10 insert table entry, we have again 10, but the physical, the frame number, we have 170 and 1. So as you can see, we have two VPN number, 10 and 10. Okay, now the issue is in the context switch, we cannot distinguish which entry is meant for which process because all the VPN is 10, 10. So if process B wants to access, it can go for here. Again, process A, when it comes here, it can go for here. So there will be a discrepancy. This is the problem with TLB. So what is the solution? To solve this kind of problems, we will provide an address space identifier ACID field in the TLB. So as you can see here, we're gonna add ACID, and for the process A we have 1, for the process B we have 2. So in this case there will not be any problem because even if the VPN number is the same, but the ACID number will provide additional information. Another case is two processes share a page. For example, if two processes are sharing the same page, this is physical frame number. So as you can see, process 1 is sharing physical page number 101 with process 2. So P1 maps this page into the 10th page of its address space, but P2 maps the page to the 15th page of its address space. So as you can see, this is 10 and this is 50. Sharing of page is useful as it reduces the number of physical page in use. So that is the other problem. This is an issue. So the other is TLB replacement policies. Objective is to minimize TLB miss rate. That is for sure. So the system we are going to use is least recently used. Okay, we are going to use this algorithm. Evict an entry that has no recently be used and take advantage of locality in the memory reference string. Let's see, these are our page frames. We have 1, 2, 3 frames. Okay, and let's say these are reference rows. Okay, these are the reference rows. Now what LRU doing, list recently used, is doing, for example, the CPU need page 7 here. Okay, 7, the data 7, for example, but 7 is not in the frame, so this assumes like miss because there is nothing in our frames, frame 1, 2, 3. So what it does is it is a miss, so 7 will be here. Next, the CPU needs 0, but as you can see 0 is not here, so it is miss and 0 will be in the second frame. Now third, we have 1, the CPU need 1, but there is no 1 here, again it is miss, so 7, 0, 1. Now here when we come here 2, now the frames are full already. Okay, the frames are full already. So what the list recently used do is we have 3 frames, so 2 is here, 1, 0, 7. So 7 is the least recently used, so 7 will be replaced by 2, then 0, 1. Those, this is also miss. Again 0, 0 is a hit because 0 is already here, a hit, so 2, 0, 1 is included here. Now 3 is not here, so what it does is we are here 3, let's check 0, 2, 1, so 1 is the least recently used, so 1 will be changed by 3 and 703 will be here. Next is 0 is already hit, so here it is a hit, so 703 will be here. Next we have 4 is not here, so what it does, we have to check. Okay, 4 is not here, so the 0 is already used, 3 is already used, so 7 is the one which is least recently used. So what it does, we're gonna change 7 here. Okay, we're gonna change 7 here, 403. Now 2 is not here, so if you see 403, 3 will be changed by 2 and 702. 3 is here, no, so this is also a miss, so 2, 4, 0, so 0 will be changed by 3. Now 0 is here, no, 3 is used, 2 is used, so the list recently used from here is 7. Okay, so 0 will change 7. Again 3 is here, it is a hit, 2 is here, it is a hit. Then 1 will be 2, 3, 0. 0 is the least recently used, so 1 will be replacing this page. Then 1, 3, 2, and 2 is a hit. Then 0, okay, so 0 will be replacing 3. Okay, because 2 is already recently used, so this one will be changed, 3 will change 2. Then 1 is a hit. So if you count the misses, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. So in this scenario we have 11 TLB misses happen. So in the nutshell, that is what TLB replacement policy. So this one is the real TLB entries, and all 64 bytes of this TLB entry, example of MIPS are 4000. So if you see here, we have 32 bits, and we have VPN, we have physical frame number, we have ACID, and we have a lot of bytes. So you can see VPN 19 bytes. Okay, 19 byte VPN. The rest reserved for the kernel. 24 byte physical frame number, as you can see, 24 bytes. System can support with up to 64 GB of main memory to the power of 24 times 4 KB of pages. Global bit, we have G, used for pages that are globally shared among processes. ACID, we have operating system can use to distinguish between address spaces. We have seen that. And coherence bit, we have C, determine how a page is cached by the hardware. And dirty bit D, we have marking when the page has been written. And the valid bit, we have V, tells the hardware if there is a valid translation present in the entry. So in general, that was the idea of chapter 19. I hope it was helpful. We have seen the TLB replacement issues. We see also LRU, least recently used, and other cases like sharing memory pages, and how ACID will help us to distinguish two VPN number, and context switch. We have seen the problem of context switch, and TLB entries. We have VPN, PFN, and other bits, and we have seen the algorithm and who handles the TLB miss in the RISC and CISC type of computers, and we have seen locality and spatial locality and temporal locality, and accessing an array. We have seen how to access and how to change. And TLB basic algorithm, we have seen that when there is a TLB miss and a TLB hit. And this is the general idea of when the CPU generates the virtual address, and it will look up in the TLB. If it is found, it is TLB hit, and it directly to physical address and found the data it needs. And if it is a miss, then we have to go to the page table. And in general, that was Translation Lookaside Buffers in chapter 19. So next time I will come with chapter 20, the next chapter. I hope this video give you an idea, some kind of concept about this chapter. So this is the Engineer Selassie from Halo Academy in Brain Boosters. Thank you so much, and we shall meet next time. Bye bye.